I'm Mani Khanuja, Principal Generative AI Specialist Solutions Architect at AWS, and I've authored 2 books on building and scaling these systems in production. Last time, we followed one request through 8 hops and found that only one of them was your GPU. So today, we go inside that one hop because something genuinely strange happens in there. How many times does your model run for a single request? The honest answer is twice, or you can say 2 stages, and these are very different from each other. They have same weights, same GPU, same line of code, and they behave so differently that they may as well be 2 separate programs that happen to share a file. One of them will happily use the hardware you're paying for. The other leaves most of it sitting idle, and there's almost nothing you can do about that from inside a single request. So which of the 2 is your bottleneck right now? That's the question this episode will answer. And nearly every confusion I see in this field comes from people treating those 2 stages as though they were one thing. And once you understand these 2 stages that your request goes through, you'll get a better understanding of identifying the latency in your request. These 2 stages are prefill and decode, which we touched upon in the previous videos. So in this video, let's start with prefill, which is simply your model reading the entire prompt that you sent it. But what does reading actually mean here? Your model doesn't read words at all, right? It only ever works with numbers. So the very first thing that happens to your prompt is tokenizing. Your text gets split into tokens, and every one of those tokens is turned into a list of numbers. That list is what we call a vector. Now stack those vectors up, one for every token you sent, and what you have is a matrix. Your prompt has become a grid of numbers, and your model's weights are matrices too. So that prompt matrix gets multiplied by those weight matrices, and out the other side come 3 more matrices. Queries, keys, and values, one set of them for every single token you sent. And that happens again in every layer of your model. 3 grids of numbers out of one prompt over and over. Every token arrived at the same moment, so nothing in there is waiting on anything else, which means every last piece of that multiplication can happen at the same time. And what you are left with is one matrix multiplied by another at a genuinely enormous scale. And here's the good news, that prefill by itself is not your blocker. Big, dense, regular matrix multiplication is exactly what your GPU was designed and built and priced for. And it can do staggering amounts of it in parallel. So prefill saturates your GPU. The Sarathi paper puts it about as plainly as you could want, saying the prefill phase effectively saturates GPU compute even at small batch sizes, which means that during prefill, you're compute bound. Your chips are genuinely busy, and the thing you're waiting on is the arithmetic itself rather than anything else. And is that bad news? Not at all. Compute bound is the good case because it means you're actually using the expensive thing you bought or leased if you are using cloud. And when all that parallel work finishes, out drops your very first token. That moment, the one your user has been staring at a blank screen waiting for, is the thing we call time to first token back in episode 1. Before we get to decode, prefill left something behind, and it is the reason any of this is affordable at all. As your model read that prompt, every layer worked out 2 things for each token, called keys and values, and it stored them. That store is what we call the KV cache. Why does that matter so much? Think about what would happen without it. Every new token has to look back at everything before it, so your model would have to recompute your entire conversation on every single step. Instead of all that, it simply reads what is already sitting in the cache from every step that came before, and then adds a single new entry of its own. One entry, that is the whole saving. So the whole arrangement is a trade you make once and then live with for the rest of the conversation. Prefill fills it once, decode reuses it. Now decode, which works completely differently. Your model produces one token and then it stops. To produce the next one, it needs the token it just wrote. Because the moment that word exists, it becomes part of the input for everything that follows it. So it runs again and again. 1 token per pass. 200 tokens of output means 200 separate passes through every single layer of your model, one after another, each one of them waiting on the one before it to finish before it is even allowed to start. You can't parallelize decode the way you could prefill, right? Every step depends on the one before it. And that single fact is what makes the second half of an answer feel slower than the first half was to read. What does that actually cost you? Instead of a matrix times a matrix, you now have a matrix times a single skinny vector. The same weights doing dramatically less useful work on every pass. And here's the problem. You still have to drag every single one of those weights out of memory in order to do that much smaller amount of work with them. Let me put that in a picture. Imagine your model's weight sitting in a warehouse a long way from the chips that need them. And every decode step sends a van out there to collect the whole lot, use it exactly once, and drive back. Those trips are what cost you. Not the lifting at the far end, the traveling and your cash makes that load heavier on every single trip. So why not keep it all close by? Because the fast memory sitting next to the compute is measured in tens of megabytes, and your weights are measured in gigabytes. They simply do not fit. The Sarathi paper describes Decode as low compute utilization precisely because it generates one token at a time per request. So Decode is memory bandwidth bound, and that phrase is worth unpacking properly because what it means is that the thing standing between your user and their next token is not any calculation your GPU has to perform. It is simply the time taken to move numbers from one place to another. Your cores sit idle. You get billed anyway. So let's put a number on how wasteful that actually is. At batch 1, a decode step costs you roughly the same whether it produces one token or 100 of them. So what happened to the other 99? Nothing at all. Your van drove the entire route out and back and delivered a single parcel. That slack is real, right? It's sitting in your system this second being paid for and delivering almost nothing. So here's the question that ought to be forming. If that trip is happening anyway, does it have to be for one request? It doesn't. And that, right there, is the entire reason batching exists. Your model's weights get read out of memory once and loaded in, and then every request that happens to be waiting can use that same load. You paid for one trip, so you may as well fill the van. That's it. That's the whole mechanism. Not a clever scheduling trick, not anything exotic, just refusing to pay twice for a read you already made. Same journey, same fuel, 32 deliveries instead of one. Now, does batching help every part of a decode step equally? It doesn't. And where it stops helping is genuinely interesting. But that's a whole module of its own, and we get into it properly later in the course. One warning before we finish, because this mistake costs people weeks, and I've watched a strong team lose a sprint to it. When engineers hear that attention is quadratic, what do? They go and optimize attention first, because it feels like the obvious lever to reach for. But at the sequence lengths most of us actually serve, it's your linear layers that dominate the runtime, not your attention. Does attention's cost grow faster? It does, and it overtakes in the end. But that means prompts far longer than most production traffic ever sees. So go and check where your time is really going before you optimize the thing that merely sounds expensive, right? And this split, one phase saturating while the other starves, is what motivates chunked prefill and disaggregated serving later on. The two papers behind today's episode are both linked below for you. Sarathi is the one that states this prefill and decode asymmetry most directly. And it's also where chunked prefill itself comes from. So it's genuinely worth your while before we reach Module 4. And Pope and colleagues, efficiently scaling transformer inference is the deeper treatment underneath all of this. Next time we get properly precise about the metrics themselves. Time to first token, time per output token, and why people confuse those two constantly, right? Bring your own dashboard to that one. See you there.